Before jumping in here and talking about some of the notation we have, working in some basic examples that we have for graph theory, I'd like to try and set the stage a little bit more here. Because unlike the things we saw earlier, things with number systems and measurement representation, along with personal finance and how voting and elections are run, things with graph theory don't necessarily have to fit the real world. It wasn't always that the problems we did in those last few sections, those last few chapters, were all the most interesting things that you possibly could have done, but you can always fall back on some real world context in which they might matter to draw some more value from them. And while you can talk about graph theory in a real world meaning, in real world contexts of things like social networking and logistics, for a lot of people, working with graph theory isn't so much about what it can be used for as it is why they might want to do it because, well, they just find it kind of interesting and maybe even kind of fun. And I know that probably sounds a little bit weird to you guys because I know you aren't necessarily the most mathematically inclined, but hey, sometimes you can do math for fun. A lot of really important math comes from riddles and number puzzles, whether these are problems like trying to figure out how to get hungry farm animals across a river in a small boat.
A man has a fox, a rabbit, and a cabbage, and he wants to get across the river, but his boat can only carry one of them at a time.
Get a bigger boat.
No, that's not an option. And here's the problem. If the man leaves the fox and the rabbit alone, the fox is going to eat the rabbit, and the same for the rabbit and the cabbage. So, how does the man get all three of his items across the river without losing any of them?
But you're ducking.
Oh, what's that now?
Stuffs the cabbage in the rabbit, and the rabbit in the fox, and he eats all of them.
That's not the answer.
Or figuring out how to fill various jugs of different sizes.
A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. You must be precise. 1 ounce or more or less will result in detonation.
Or just playing an actual game of Sudoku or 2048. A lot of good mathematical logic is hidden inside of games and can be built further off of them. For a different sort of example, we can fall back on an anecdote of Feynman's, where he was talking about a discovery he made that led to a Nobel Prize that came from a situation in a cafeteria, where what he says is, I was in the cafeteria and some guy fooling around throws a plate in the air. As the plate went up in the air, I saw it wobble, and I noticed the red medallion of Cornell on the plate going around. It was pretty obvious to me that the medallion went around faster than the wobbling. I had nothing to do, so I started to figure out the motion of the rotating plate. Then I thought about how the electron orbits start to move in relativity. Then there's the Dirac equation in electrodynamics. And then quantum electrodynamics. The whole business that I got the Nobel Prize for came from fiddling around with the wobbling plate.
I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell, possibly. It doesn't frighten me.
To be sure, this doesn't necessarily mean that every idle bit of thought you have while eating lunch could, with enough work, earn a Nobel Prize, but it does point out that sometimes very beautiful and meaningful things come from what seems, in the moment, like nothing at all. And for that matter, when we get told that we need to learn something simply for the fact that it is useful, for example, if I tell you something is useful on an exam, you're more likely to forget about it immediately afterwards. That is, immediately after it ceases to be useful, or, in our context, immediately after the exam. When you learn something because you enjoy it, on the other hand, you're probably a bit more likely to have it stick in your mind. It might stay a little bit longer. For a completely different sort of example, I still remember both how to get to and beat the first real boss of Dark Souls, the first game that came out years and years ago, not because it's a particularly difficult game, or because I had some strange ambitions to be one of those internet celebrities who beats the games using electrified bananas, but because I liked the game. and I stuck with it because I enjoyed the process of working through the game. And as you can see, that's really all there is to it. Where I'm being a little bit long-winded here in this introduction.
Hey! You want to focus on the problem at hand?
Because, again, when we're talking about graph theory, we're not necessarily talking about something that has to fit the real world in a necessary and powerful way at first sight. Because the genesis of graph theory, as it were, is a riddle. It's a riddle from the 18th century in Prussia, specifically Königsberg, which today is Kaliningrad in modern Russia, that is without the P because Prussia is no longer a country, where the city is situated with two large islands, Neidhof and Lomps. Sorry, I'm going to mispronounce those. My Prussian is not very good. Connected to the rest of the city via a system of 7 bridges over the Pregel River, where, in seeing this diagram, in seeing this map of the city, some people came to wonder, hey, is there a path you can take through the entire city such that you will cross all of these 7 bridges exactly one time? And this is a fun little problem people worked on. It's a fun little riddle, just like some of those other ones I mentioned earlier, where in particular in 1736, a young Leonard Euler, who I have mentioned before, like I said, he's kind of important, came to the conclusion that when working with this problem, there wasn't actually a solution. You weren't going to be able to cross all 7 of those bridges exactly once on a route through the city. And in studying it, he made some important pieces of abstraction. He gleaned some information there that was a little bit unexpected, that when you're talking about making your route through the city, the only parts of the city that matter are the bridges, because they're the only parts that have any restriction on them. So what he envisioned was taking that map of the city and just sort of abstracting out all of the stuff that's going on there, except for the river and the bridges, just focusing on the parts that mattered for what he was looking at. Where from there, people would then take those blobs of abstract Prussian information and make them even more abstract by replacing the regions, the areas between the bridges, with dots, and the bridges connecting them with lines. So they created the first graphs. And was it truly entirely necessary that the Königsberg Bridge problem be solved? Not really, because you don't have people who are traveling through a city that can only cross a bridge once. They probably don't even care about which bridges they're crossing in what order. They just need to get from point A to point B, maybe through point C, depending on what bridges are where. They're going to pick the shortest route they can, which is something else we'll talk about with graph theory. That's another kind of problem we can look at, is finding optimal shortest paths between locations, thinking logistically again. But, they wouldn't go out of their way to cross every single one. If they crossed one more than once, who cares? It's just a bridge. But what came out of this, what came out of working through this problem, thinking in terms of very abstract senses of geometry, would become both graph theory, as I mentioned, and another very important modern mathematical field called topology that we're not going to see in this class, but that goes in some very strange and interesting directions for people who are willing to spend a lot of time with that stuff. Where, in the case of graph theory, we call the sequence there of making that abstraction into just points and lines, just those points and lines themselves, a graph, where each point is called a node or vertex, and the line segments between them are things that we call edges. So with this representation, we have that the vertices represent parts of the city, and the edges are the bridges, but we'll see that bridge has a slightly different meaning in graph theory later on. Don't worry too much about that just for now. Where a bit of personal history here, if you can't tell based on a little bit of excitement I have here and the fact that I'm going in a bit more detail than I sometimes might without getting into too much historical context, I actually did a fair bit of graph theory research in undergrad. It was really all the research that I have done, so I'm very excited to get the chance to teach this to a class. I haven't been given that chance before, and hopefully you're all able to enjoy this. Hopefully you're all able to get something out of this. But I do have one more important rhetorical question to ask here before we actually get into what some of this stuff means. Do I expect you all to like this as much as I did? And unfortunately, I have to be reasonable with this and understand the answer there is probably not. Because like I said, this is a bit weird. Even for a general math class, pun completely unintended there, but for any other math class, this isn't the most normal topic, and especially for this one where we've been very grounded up to this point, it's a little strange. But the real important thing I'd like you to take from this very long-winded introduction is that I think it's important to give time to studies that you are interested in simply for the fact that you are interested in them. Maybe they go somewhere really beautiful and meaningful. Maybe they don't. But I can guarantee to you that you will give yourself the very best chance of taking them somewhere special because they are special to you. Anyway, that's enough general things here. I don't want to say general math again quite so soon. Next, we'll actually start learning a little bit more about how these things work.